Hey everyone, and welcome back for another deep dive. This time we're looking at the really tough stuff that comes with keeping mining robots running in space.
Especially asteroid mining.
Yeah, asteroid mining. We've got a great chapter to dig into today. It's called Thermal Control and Radiation Shielding for Asteroid Mining Equipment. Catchy, right?
Definitely. And it's not just about, the tech side of things.
Right.
This is about the big picture. Can we actually make asteroid mining a thing?
So we're not just talking about a space Roomba getting a sunburn.
Exactly. We're talking about an industry, a whole new way of doing things.
Wow. Okay, so big stakes then.
Absolutely. Think about it. You're on an asteroid, no atmosphere, the sun is just beating down.
It's hot. I mean,
So we-
really hot, like over 100 degrees Celsius.
Oh, wow. Yeah, that's way hotter than my oven.
It is.
But then what happens? The asteroid rotates, right? So it's not always in the sun.
Right. And when it rotates, you're in shadow. And then the temperature plummets
Oh, wow.
down to like Medicus Hunting of 50.
Yeah.
Oh my gosh, that is a huge swing.
It is. And on some asteroids, that rotation is super slow.
So it could be stuck in either extreme for a long time.
For days.
Oh, wow. Days. My phone would just die, I think.
Yeah.
I mean, more than die.
It wouldn't stand a chance.
No.
Yeah?
So what happens to like actual mining equipment with those kinds of temperature extremes?
Well, think about it. The metal parts are constantly expanding and contracting. It's like if you bend a paperclip back and forth over and over
Right,
again.
it eventually snaps.
Exactly. And that's what we call material fatigue. It can
Yeah.
really mess things up.
Right. And I'm guessing the electronics don't love those temperatures either?
Not at all. Electronics are very sensitive to temperature. Too hot, they fry. Too cold, well, you've got battery drain malfunctions.
Makes sense.
And then there are the lubricants. All those moving parts need lubricants to, move smoothly.
Right.
But at negative 150 degrees Celsius, they freeze solid.
So everything just grinds to a halt.
Pretty much.
Okay. So how do engineers even begin to design equipment that can survive these conditions?
Well, it's a two-pronged approach. Passive thermal control and active thermal control.
Okay, break that down for me.
Think of passive control as dressing for the weather.
Okay, got it.
And active control is like having a personal thermostat.
I like that analogy. So for passive control, what kind of spacesuit are we talking about?
One of the most common things is multi-layer insulation, or MLI.
MLI. Okay.
It's basically a high-tech thermal blanket. You have all these layers of reflective material, and between the layers, a vacuum.
Wait, a vacuum? Isn't space already a vacuum?
It is, and that's exactly why it works. We're using the vacuum of space to prevent heat transfer.
Oh, that's clever.
It's like a super efficient thermos. And then there are those shiny coatings you see on spacecraft.
Yeah, those definitely seem to be doing something important.
They are. Those coatings are designed to either reflect sunlight to keep things cool or trap heat to prevent freezing.
So it's all about managing the energy flow, right?
Exactly. And then we have radiators.
Radiators, like in a car.
Kind of. They're those big flat panels you see on spacecraft. And they radiate excess heat out into space.
So they're basically venting heat to keep the equipment from overheating.
Exactly.
Wow. Okay, so we've got our robots bundled up in MLI, wearing their reflective sunglasses, sweating it out through radiators.
It's a pretty good picture.
What about active thermal control? What kind of high-tech thermostat are we talking about here?
Active systems are all about adjusting to changes in real time. For example, thermal louvers. They act like adjustable window blinds, opening and closing to regulate heat flow.
Oh, I like that.
Open the blinds when it gets too hot, close them when it's too cold. And then there are heat pipes.
Heat pipes.
They circulate heat efficiently throughout the spacecraft. So, moving it from hot spots to cooler areas or to the radiators.
So it's like a circulatory system for the spacecraft.
Kind of, yeah. And for those really, really cold situations.
Like those negative 150 degrees.
Exactly. We can use things like electrical heaters.
Just add heat directly.
Makes sense, right? And then there are these things called phase change materials.
Phase change. What's that?
They act like thermal batteries. They absorb heat when it's warm and release it when it's cold, smoothing out those temperature extremes.
Okay, that's pretty cool.
It is.
Wow, so maintaining a stable temperature in space is quite the challenge.
It is.
But it's not just about the temperature, is it? There's something else out there, something invisible and dangerous.
You're talking about radiation.
Radiation. Yeah, I have a feeling this is where things get really interesting.
It is.
So tell me, what kind of radiation are we dealing with out in space?
Well, you've got cosmic rays. These are high-energy particles coming from outside our solar system.
Okay, so that's constant bombardment from deep space.
Right. And then you have solar particle events. These are bursts of energy from the sun. Think solar flares, but with a lot more radiation.
And I bet when those hit an asteroid?
It creates secondary radiation, like a ricochet effect.
Oh, wow. So it's radiation on top of radiation.
Pretty much. And all of this is hitting our mining equipment.
Yikes. So what kind of damage does this radiation cause? I'm guessing it's not good.
Not good at all.
Yeah.
Electronics can glitch, suffer permanent damage.
And that's just the electronics. I'm guessing other materials are affected too?
Absolutely. Radiation can weaken materials, make them brittle.
Mm.
And then there are the sensors that those robots use.
To navigate and find resources.
Exactly. Radiation can disrupt those too, creating noise in the readings, making the data unreliable. It can even essentially blind the robot.
Oh, wow. So we're talking glitching robots, weakened structures, blind sensors. This is starting to sound like a horror movie.
It's a challenge for sure.
So how do we protect our precious equipment from all this radiation? I'm picturing thick layers of lead like they use in X-ray rooms.
You're on the right track. Lead is great at absorbing radiation,
Well,
but
yeah.
it's heavy. And every kilogram we launch into space adds to the cost.
Right, of course. Weight is a big deal in space.
It is. So we're also looking at lighter materials, polymers, composites, especially those rich in hydrogen.
So using the lightest materials possible. Any other clever ways to shield against radiation?
Well, there's the Whipple shield. It's a multi-layered barrier that breaks up radiation energy. Think of it like a bulletproof vest. It spreads the impact.
Interesting. So not just about brute force, but clever design.
Hmm.
What about using the asteroid itself as a shield?
Now, that's a really interesting idea.
Yeah.
We could potentially bury equipment under layers of asteroid regolith.
Oh, using the environment itself as a shield.
Exactly. But passive shielding is only part of the solution. What about active shielding?
Active shielding, so like Star Trek force fields?
Not quite force fields, but we are talking about manipulating energy,
Hmm.
using things like electromagnetic fields to deflect those charged particles away from the equipment.
Wow, okay, so that's still pretty futuristic.
It is. There's also the concept of plasma shields, which are layers of ionized gas that can absorb or redirect radiation. And then there's something even more out there.
More futuristic than plasma shields.
Possibly. Self-healing materials.
Self-healing.
Yeah, materials that can repair radiation damage over time.
That sounds straight out of science fiction.
It does, but it's an area of active research.
Wow, okay. So we've covered thermal blankets, reflective coatings, radiators, thermal levers, heat pipes, phase change materials, and now a whole array of shielding options. My head is spinning.
It's a lot to take in.
It is. It seems like an incredible amount of ingenuity goes into just surviving in space, let alone actually mining anything.
It does, but the amazing thing is that these are not just theoretical solutions. We have real missions proving that this can be done.
Oh, tell me about them. Give me some real-world examples.
Well, there's Japan's Hayabusa 2 mission to the asteroid Ryugu.
Hayabusa 2. They actually brought back samples.
They did. And Ryugu had those extreme temperature swings we were talking about.
Why did they manage that?
They used a combination of passive and active approaches, MLI, thermal coatings, even autonomous thermal control algorithms.
Wait, so the spacecraft was adjusting its own temperature in real time?
Yeah, that's right.
That's incredible. What other missions are pushing the boundaries of thermal control and radiation shielding?
Well, there's NASA's OSIRIS-REx mission to asteroid Bennu.
OSIRIS-REx, yeah. I remember hearing about that one.
Their big challenge was protecting their sensitive instruments from all the cosmic radiation.
Did they just use a ton of lead shielding?
They did use some, but they also focused on radiation-hardened electronics and clever mission planning.
So designing electronics that could take more of a beating.
Exactly, and timing things to minimize exposure during solar storms.
Wow, so it's not just about the hardware, but also about working with the environment as best you can.
Exactly.
This is all incredible. I can't believe how much we've already covered, and it seems like we're just scratching the surface. We've gone from scorching heat to freezing cold, from passive insulation to the possibility of active force fields, from theoretical challenges to real-world missions tackling these problems head-on.
It is a fascinating field.
It is. But this is just the beginning. In Part 2, we'll delve deeper into the cutting-edge technologies and innovative solutions that are paving the way for a future where asteroid mining becomes a reality.
We'll talk about smart materials, nanostructured shields, in-situ resource utilization, and even swarms of tiny robots.
Sounds amazing. Stay tuned, everyone. Welcome back, everyone, to our deep dive into the world of asteroid mining. Last time we were talking about all the crazy things those mining robots have to deal with. The heat, the cold, the radiation.
It's enough to make you want to stay put right here on Earth.
Right. But as we learned, there are some really smart people working on solutions. And today we're going even further, looking at those cutting-edge technologies that are making this whole thing possible.
We're talking about stuff that was once just science fiction.
Okay, I'm ready. Tell me about these technological marvels. What's on the horizon?
Well, one area that's super exciting is smart materials.
Smart materials. Okay.
These are materials that can actually change their properties based on the environment they're in.
So like what, give me an example. How would that work for, say, a spacecraft?
Okay, so imagine a coating on your spacecraft that becomes more reflective when it's exposed to a lot of sunlight.
So it helps keep the equipment cool when it needs to.
Exactly. Or a material that changes its insulation properties depending on the temperature.
So it's like the spacecraft has a built-in temperature regulator constantly adapting.
That's the idea. And when it comes to radiation, there are some big breakthroughs happening with nanostructured materials.
Nanostructured. Okay, remind me what that means.
We're talking about engineering materials at the atomic level.
Wow. So like super tiny.
Super tiny. And by working at that scale, we can create shields that are way better at blocking radiation.
Than what we use now.
Way better. And a lot lighter, too.
Okay, so that's smart coatings that can adjust to the temperature and nanostructured shields that block radiation. What else? What other tricks are we working on?
Well, one thing to think about is that launching stuff from Earth is really expensive.
Yeah, no kidding.
So why not use what's already out there?
You're talking about using resources from the asteroids themselves.
Exactly. We call it in situ resource utilization, or ISRU.
ISRU.
Oh.
Catchy. So what kind of resources are we talking about? What's on the menu?
It's a pretty diverse menu. Some asteroids have tons of metals like iron and nickel, perfect for construction. Others have water ice.
Water ice. That's right. We talked about that before. You could break that down into hydrogen and oxygen.
Exactly. And that gives you rocket fuel.
So instead of bringing fuel from Earth, we could just set up a refueling depot in space.
It would be a game changer for deep space travel. And with 3D printing getting better all the time, we could even build structures in space using those asteroid materials.
Wow. So instead of just quick missions, we could have actual outposts throughout the solar system. That's amazing. But it's not just about building big structures, is it? What about all those tiny robots I keep hearing about?
Ah, yes. Swarms of tiny robots, each one with its own thermal control and radiation shielding.
Working together to mine the asteroid? What's the advantage of using lots of small robots instead of a few big ones?
Well, they can cover more ground, get into tighter spaces, and adapt to changing conditions more quickly. It's kind of like a team of ants all working together.
I like that analogy.
Okay.
So we've got smart materials, nanostructured shields, ISRU, and swarms of tiny robots. It's
Yep.
like we're using every tool in the toolbox.
It's a pretty amazing time to be working in this field.
It sounds like it.
Uh-huh.
But are there any examples of how these technologies are being used right now? Besides those missions to Ryugu and Bennu, I mean.
Oh, absolutely. The International Space Station is a great example. It's been up there for over 2 decades, and it's basically a giant experiment in thermal control and radiation shielding.
That's right. They have to keep those astronauts safe and comfortable.
Exactly. And they've done it with a combination of passive and active systems. It's a real testament to what we can do.
What about protecting the astronauts from radiation?
They use a variety of shielding materials. Water, polyethylene, even the station's structure itself provides some protection.
It's incredible how much technology goes into something we often take for granted. What about other missions? Anything using these technologies in deeper space?
Definitely. Think about the Curiosity rover on Mars.
Oh yeah, that little guy's been roving around for a long time now.
Over a decade. And it has to deal with extreme temperatures, dust storms, radiation. It relies on some pretty sophisticated thermal control to keep everything running.
Wow. Okay, so looking ahead, how important will these technologies be for future missions?
They're going to be crucial. Take NASA's Artemis program, for example. They're aiming to put people back on the moon, and they're going to need advanced thermal control and radiation shielding to do it. We're talking about long-duration missions here.
Right, not just quick trips. So it seems like we're really on the verge of something big, a new era of space exploration.
I think so. These technologies aren't just about surviving in space. They're about thriving.
And opening up a whole new world of possibilities.
Absolutely.
But it's not just about robots and spacecraft, right? These innovations can benefit us here on Earth, too.
That's a great point. A lot of what we learn in space ends up having applications here on Earth.
Like what? Give me an example.
Well, Take thermal insulation. What we've learned about insulating spacecraft has led to more efficient insulation for buildings.
So that's saving energy and helping fight climate change.
Exactly. And the same goes for radiation shielding. The technologies we develop for space can be used to improve radiation therapy for cancer patients or to protect workers in nuclear power plants.
It's amazing to think about that connection, how exploring space can make life better here on Earth.
It really is.
But before we get too carried away with all the possibilities, I think we need to talk about the big elephant in the room, the economics of asteroid mining.
It's not just about the technology, right?
Exactly. We can dream about all the cool things we could do, but at the end of the day, it has to make financial sense. So in part 3 of our deep dive, we're going to get down to the dollars and cents.
We'll talk about the potential resources, the market forces at play, and the hurdles that stand in the way of turning this cosmic dream into a financial reality.
Stay tuned, everyone. It's going to get interesting. And we're back for the final part of our deep dive into asteroid mining. We've talked about the extreme conditions, the tech, but now it's time to get down to business.
The economics of it all.
Exactly. So let's start with the basics. What kind of valuable resources are we actually hoping to find on these asteroids?
Well, some asteroids are packed with precious metals: platinum, gold, iridium.
Oh, wow, that's the good stuff. What are those used for, mainly?
All sorts of things: electronics, jewelry, medical devices, industrial catalysts, you name it.
Okay, so high-demand stuff then.
Mm.
Anything else on those asteroids?
Oh yeah, tons of stuff. Some have huge amounts of water ice.
Water ice. Right, we talked about that in part 2. You can use that for fuel, right?
Exactly. Break it down into hydrogen and oxygen, and you've got rocket fuel.
So we could basically have gas stations in space.
That's wild. What about building materials? Anything like that? You bet. Some asteroids are full of iron, nickel, silicon, all the essentials for construction.
So we could build habitats in space, research outposts, maybe even factories using asteroid materials.
Potentially, yeah. It's all about figuring out how to make it work.
Okay, so there are definitely resources out there.
Mm-hmm.
But is there a market for them? I mean, who's going to buy all this stuff?
Well, the space industry itself is a big potential customer. They're going to need all sorts of things for future missions: fuel, materials, life support.
Right, of course. Makes sense. What about industries here on Earth? Are they interested in these space resources?
Oh, yeah, definitely. The electronics industry is always looking for rare earth elements. They use them in everything these days: smartphones, computers, you name it.
So we could be bringing back stuff that's in high demand right here on Earth. What about renewable energy? I feel like they're always looking for new sources of materials, too.
Absolutely. They need platinum and other metals for things like solar panels and fuel cells.
Okay, so there's a market for all this stuff, both in space and here on Earth. But here's the big question. How do we actually get those resources back?
Yeah, that's the tricky part: transportation. Launching anything from Earth is expensive.
Yeah, no kidding. So it's not just about mining the asteroids, it's about getting the stuff back in a way that makes financial sense.
Exactly. And that's where a lot of the innovation is happening. Reusable spacecraft, space-based refineries, even things called space tugs.
Space tugs, what are those?
They're basically spacecraft designed to tow big payloads of asteroid material. They could bring it to a processing facility in Earth orbit, or maybe even all the way back to the surface.
It's like cosmic cargo ships.
Pretty much, yeah. But of course, all this innovation is expensive.
Right, no such thing as a free lunch in space.
Definitely not. Asteroid mining is high risk, high reward.
Got to spend money to make money, right? But what about the legal side of things? Who owns these asteroids anyway?
That's a good question. The Outer Space Treaty doesn't really address asteroid mining specifically.
So it's kind of a gray area.
Yeah, a bit of a Wild West situation right now. But countries are working on establishing some clearer guidelines.
Makes sense. You don't want everyone just grabbing whatever they can.
Exactly. It's got to be sustainable. So it sounds like there's still a lot to figure out. Where do you see this whole thing going in the future? What's your prediction?
Well, I'm optimistic. I think asteroid mining has the potential to be huge, but it's going to take collaboration, innovation, and a lot of hard work.
And maybe a little bit of luck, too.
Maybe a little bit, but who knows? Maybe someday it'll be as common as oil drilling or coal mining, powering our economies and pushing us further out into the universe.
Wow, that's quite a vision. It's exciting and a little bit scary at the same time.
It is.
Well, thanks for taking us on this deep dive. I've learned so much.
It's been my pleasure. Always happy to talk about this stuff. It's clear that asteroid mining is a complex issue with a lot of moving parts, but it's also a field full of incredible possibilities. And who knows, maybe some of our listeners will be the ones making those possibilities a reality. That's all for this deep dive. Thanks for joining us and keep looking up.